Hey guys, hope you're all doing good and welcome to a new video. So today we are going to be discussing the results that we obtained by running the turbocharger simulation. To get started, I'm going to be discussing the post-processing results. So here I have 4 videos. On the top left we have the velocity magnitude, and then on the top right we have a cut plane that's going to show the pressure. Bottom left we have pressure acting on the impeller surface, and finally a 3D model of the entire turbocharger so that you get some context. So let me first play this video, and as it's playing I'll explain some important features. Right, so here you can see that the turbine is slowly starting to rotate, right, and you can see that in the 3D diagram as well. And as it's rotating, you can basically see that there are certain areas of higher pressure, mainly where the jet hits the impeller. Right, so this is the primary simulation. But there are a lot of things that you can actually see from this. So for example, here you can see that the velocity jet has started, but the impeller has some inertia which it has to overcome, and it accelerates slowly. So let me just show that once again. See that initially impeller is not rotating, but then after some point it does. When the impeller gets a torque above its threshold, it starts to rotate and it slowly starts to accelerate. And similarly in this plot, you're actually looking at the pressure on the impeller surface. Now this actually tells you a lot of important insights. First is you can see that the impeller is not uniformly loaded. One side of the impeller is always loaded more than the other side, so there is asymmetrical, so the loading is basically non-symmetrical. This might be relevant for FEA simulations. So you can take this pressure force, so you can take this pressure field and get a pressure force and use that as a boundary condition for a modal analysis to kind of understand how the mode shapes vary at different RPMs, right? But that being said, the simulation is fairly coarse. As you can see, we would definitely need to run the simulation a bit more finer if we want to do some if we want to get engineering data out of it. So here we are also looking at pressures. Now you can see that there is regions of high pressure and low pressure zones, and this is also a very typical plot. Mainly because you are starting to see this recirculation zone here that actually sits exactly on the back side of the impeller, Now as far as cell count is concerned, you can see that we have this really fluctuating plot, but don't let that fool you. If you look at the y-axis, you can see that the cell count is hardly changing. That's because this particular case that does not use adaptive mesh refinement. Then you might ask why the cell count is actually changing. Well, that's very simple. Converge create computational mesh every time step, correct? So depending upon the position of the impeller, the mesh created is going to be slightly different, which is going to lead to slightly different cell count. Now one of the things that you need to look at in these type of simulations is convergence. So here we are running a simulation for about 0.06 seconds, and you can see that the fluid angular velocity has almost converged. But it's very important to not get fooled by this plot and many such similar plots. For example, in this plot you're looking at angular velocities in the fluid region along the x-axis, y-axis and z-axis. So the way this is computed is fairly straightforward. In each of the cell there is x, y and z component of velocities. So what you can do is you can calculate an angular velocity based on this velocity with respect to x, y and z axis, and you can average that for the entire domain, and that is what you're plotting, right? So for your entire domain you have one data point. So as you plot this one data point as a function of time, you get 3 such curves. Looking at this, one might actually say that, hey, the simulation has converged and there is no need to run that. This is one of the classic mistakes that people make, especially in these type of simulations. Now the reason why I'm saying that this is wrong is not because you should not check for convergence in angular velocity values. It's because you should look at other parameters as well. So let's look at, for example, torque generated on the turbine. Now you can see that the torque generated, you can see that there is a lot of fluctuation, but there is definitely a mean or an average value for that fluctuation. This plot also indicates that convergence might have reached. Okay, so let's look at a few more plots. If you look at mass flow rate at the inlet and outlet, that has also converged, which basically says that the simulation has converged. But the interesting thing that we see, which tells us that the simulation has not converged, is the angular velocity of the turbine. Now this can be visualized from a file called fsi_object.out, which contains the angular velocity of the turbine. Now here you can see that this is continuously increasing, meaning the turbine is still in its accelerating phase. Now in this particular case, You can define convergence in two ways. If you are just looking at how the inlet outlet mass flow rate is changing, or how the flow pattern is changing inside the entire casing, then running the simulation up to 0.06 seconds is actually more than enough. And say that you just want to understand how much moment or how much torque it takes for you to rotate the impeller, then you already have that value here. You don't need to run the simulation longer. But in case you want to run the simulation till the turbine picks up its full speed, you have to run the simulation much longer. How long? Well, that calculation is fairly simple. So the turbine in the turbocharger typically spins around 150,000, 100,000 to 150,000 rpm. Now end time for the current simulation is 0.06 seconds, right? And the angular velocity that we got at 0.06 seconds is 900 radians per second, and if you convert that to rpm, it's just 8598. So in order for this to reach to 150,000 rpm, now we are assuming that 150,000 rpm is the final value. If that is the case, then you are looking at a simulation time of 1.04 seconds. So you can say that if you run the simulation anywhere between 1 to 1.5 seconds, you can expect the angular velocity to converge. Now we really don't know this until we run the simulation, but this is an important point that we felt like you should know. Alright, so I hope through the last two videos you learned how to perform fluid structure interaction, and you also gained some insights on how to understand if the simulation results has converged or not. With that, I would like to conclude this video. Thank you. Bye.